Hello, in this lecture we find out the area of the green semicircle using two different methods. In the drawing we have two semicircles. This is the white semicircle and this is the green semicircle. In addition, we know that this is 9/7 AC. This is equals to 5 units in its length. This is 9/7 CB. This is equals to 1 unit in its length. And again, our mission is to find out the area of this green semicircle. So we start with the first method, and we'll join points B and P together by straight line. By joining points B and P, we create a peripheral angle APB. This is peripheral angle APB. So I'll copy the white semicircle if the peripheral angle APB that is inside the white semicircle, and we will implement rule 7 on the white semicircle. So actually, this is the white semicircle that I copied from the original drawing, and this is peripheral angle APB. AB is the diameter of this semicircle, so I'll write it down. AB is the diameter of the white semicircle. So in the drawing we have peripheral angle APB. This is peripheral angle APB, and it is subtended on AB, that is the diameter of this semicircle. So here we can implement rule 7. I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equals to 90 degrees. So here we have a circle. AB is the diameter of this circle, and we have here peripheral angle ACB that is subtended on AB, that is the diameter of the circle. Therefore, peripheral angle ACB equals to 90 degrees in its size. So whenever you have a peripheral angle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APB that is subtended on AB, that is the diameter of the semicircle. Therefore, peripheral angle APB must be equal to 90 degrees in its size according to rule 7. So this angle, peripheral angle APB equals to 90 degrees in its size according to rule 7. In the next step, we'll join points C and P together by a straight line, those 2 points. So actually, by joining point C and P, we created here in relation to the green semicircle, we created here peripheral angle ACP. This is peripheral angle ACP that is located inside the green semicircle. So I'll copy the green semicircle with its peripheral angle ACP, and again we'll implement rule 7 on the green semicircle with its peripheral angle ACP. So actually, this is the green semicircle that I copied from the original drawing, and this is peripheral angle ACP. So in this green semicircle, we know that AP is the diameter of this semicircle. So I'll write it down. AP is the diameter of the green semicircle. And angle, peripheral angle ACP is subtended on AP, that is the diameter of this green semicircle. Therefore, according to rule 7, peripheral angle ACP equals to 90 degrees in its size. So this peripheral angle ACP equals to 90 degrees in its size according to rule 7. Okay. So if we focus on the original drawing, this is angle A, and this angle A, this angle A is a common angle that belongs to both triangles. It belongs to the green triangle APC, you can see, and this angle A also belongs to triangle, the right triangle APB. Therefore, angle A is a common angle that belongs to both triangles. So we define the common angle, angle A, as alpha. It exists on both triangles. So we define the common angle, this angle, as alpha. So in the right triangle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees equals to 180 degrees. So I do the same process here because maybe it is not correct because of the green color. So here we'll define angle A, that is a common angle that belongs to both triangles, as angle alpha. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, which is the sum of the angles in any triangle. So in the next step, I'll copy the right triangle APB and this green right triangle APC in a new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. So actually, this is the green right triangle APC that the copies from the original drawing, and this is the white right triangle APB that are also copies from the original drawing. So in the next step, we will prove that those two right triangles are similar to each other according to angle similarity rule. So we will prove that this right triangle APB is similar to the right green triangle APC, this right triangle APC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle APB. In the right triangle APB, and it is equals to this angle, that is actually angle ACP. In the green triangle APC, repeat again, angle APB in the white triangle equals to angle ACP in the green triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha. Angle alpha belongs to both triangles, so we can write out that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to angle alpha as it belongs to this right triangle, it will be defined as angle PAB, and it equals to itself. So if we relate to angle alpha as it belongs to the green triangle, it will be defined as angle PAC. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle ABP in the white triangle APB, and it is equal to this angle, that is actually angle APC in the green triangle APC. So repeat again. Angle ABP in the white triangle equals to angle APC in the green triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the three angles in this green right triangle APC are correspondingly equal to all the three angles in this right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. So the right triangle APB is similar, this is the sign of similar, to the right green triangle, triangle APC, according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. But before that, what is the length of side AB? From the drawing, it is very easy to see that side AB in total equals to 5 plus 1, that is 6. Again, AB equals to 6 units in its length, so I write it down. This is side AB, and it is equals to 6 units in its length. And it is given us the equation that side AC equals to 5 units in its length. So from the fact that those two right triangles are similar to each other, we will derive that side AB in the white triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. Repeat again. We will derive that side AB in the white triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. AB equals to 6 over AP. AP is the missing side, so we leave it as it is. And it is equals to AP over AC. AC is 5. So in total we actually found out that six over AP equals to AP over 5. Here we cross multiply this equation and we get that 5 times 6, that is 30, equals to AP times AP, that is AP squared. So actually found out that AP squared equals to 30. We take a root out of this equation and finally we get that the missing side AP equals to the square root of 30 units in its length. AP equals to the square root of 30 units in its length. But we already found out that AP is the diameter of this green circle. If AP is the diameter, it means that AP over 2 is the radius of this green circle. So we define the radius of this green circle as R. So the radius R of the green semicircle must be equal to the diameter AP over 2. And the diameter AP is square root of 30. Therefore, square root of 30 over 2 is the radius of the green semicircle. Repeat again. The radius R of the green semicircle equals to square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of any semicircle equals to the area of the circle over 2. Therefore, it must be equal to pi r squared over 2. So the area of the green semicircle must be equal to pi r squared over 2. So it is pi times r. R is square root of 30 over 2, therefore r squared is square root of 30 over 2 squared divided by 2. So here we'll open the brackets of this expression and get that the area of the green semicircle in total equals to pi square root of 30 square is 30 and over 2 square is 4. So square root of 30 over 2 square is 30 over 4 divided by 2. And we have pi, and 30 over 4 over 2 is 30 over 4 times 2. So in conclusion, I should find out that the area of the green semicircle equals to 30 over 4 times 2. 30 over 2 is 15. Therefore, this expression in total equals to 15 pi over 4 square units. 15 over 4 is 3.75. Therefore, this expression in total equals to 3.75 pi square units. That is actually equals to 11.78 square units. Okay, repeat again. We actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. So we finished with the first method. In the next step, I'll explain to you how to find out the area of this semicircle, green semicircle, according to the second method. In the second method, we'll join points B and P together by a straight line. By joining points B and P created here in relation to the white semicircle, we created here peripheral angle APB. So I copied the white triangle the white semicircle with its peripheral angle APB in the new page, and we implement on the white semicircle rule 7 exactly as we did in the first method. So actually, this is the white semicircle that I covered from the original drawing with its peripheral angle APB that was created by joining points B and P together by a straight line. We know that AB is the diameter of this white semicircle, so I'll write it down. AB is the diameter of this white semicircle, and we have here peripheral angle APB. This is peripheral angle APB that is subtended on AB, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that is subtended on the diameter of the semicircle or the diameter of the circle or the semicircle must be equal to 90 degrees in its size. Therefore, this peripheral angle APB must be equal to 90 degrees in its size according to rule 7. So here BP, line segment BP is perpendicular to PA. Again, line segment BP is perpendicular to PA because this angle equals 90 degrees. And PA is the diameter of the green semicircle. If PA is the diameter, then the radius must be half of it. So if this point O is the center of the green semicircle, it means that PO must be the radius. Again, if point O is the center of this semicircle, it means that PO must be the radius of the green semicircle. So I'll copy point O from this from the green semicircle to a new page with the green semicircle. So I copy the green semicircle with line segment BP and point O that is located on the diameter AP, and we analyze the green semicircle. So we already found out that peripheral angle APB equals to 90 degrees in its size according to rule 7. So we'll define the radius r of this green semicircle. We'll define the radius of this green semicircle as r. Therefore, PO equals to r. So actually, this is the green semicircle that I copied from the original drawing. Point O is the center of this semicircle, therefore PO is the radius of the semicircle. This is equal to R according to our definition. And this is line 7 BP that creates 90 degrees with the radius PO. Again, line segment BP creates 90 degrees with the radius PO. Why? Because we have already found out that angle APB equals to 90 degrees in its size. Again, we have already found out that according to 7, angle APB equals to 90 degrees in its size. It means that line segment BP creates 90 degrees with the radius PO of this green semicircle. Therefore, we can implement here rule 1. I'll repeat quickly on rule 1, and before that, I'll copy also the diameter AB to the new drawing. This is the diameter AB of the white semicircle. So here we can implement rule 1 because we have line 7 BP creates 90 degrees with the radius PO of this green semicircle, and therefore we can implement here rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. According to rule 1, only a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have the radius OM that equals to R. Line segment AB is perpendicular to the radius MO. Again, line segment AB is perpendicular to the radius MO, and therefore according to rule 1, this line segment AB must be defined as a tangent. So whenever you have a line segment that is perpendicular to the radius, then the line segment must be defined as a tangent. Therefore, AB is a tangent that is perpendicular to the radius MO at point M, and therefore according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So we can implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP that is perpendicular to the radius PO, and therefore according to rule 1, line segment BP must be defined as a tangent to the green circle. Okay, so this is line segment BP, that it must be defined as a tangent to this green semicircle. Why? Because it is perpendicular to the radius PO at point P. Therefore, line segment PB must be defined as a tangent to this green semicircle at point P, according to rule 1. So here in the drawing we have from the common external point B, we have tangent BP to the green semicircle. Tangent BP is tangent to this green semicircle at point P. And here we have also from the same common external point B, if we draw a straight line from the common external point B towards the semicircle, it cuts the circle 2 points. It cuts this green semicircle 2 points, C and A. Again, for the common external point B, we have chord CA, And we also have, from the same common example point B, we have tangent BP to this green semicircle. Tangent BP is tangent to this green semicircle, it's point P. Therefore, we can implement here rule 10. I'll repeat quickly on rule 10. According to rule 10, first of all, rule 10 is true in any circle. So in any circle, this can be any circle. If AB is the chord, you can see that AB is the chord of this circle, and PT is tangent to this circle at point T. Then in this drawing, the following equation will be true. PT square equals to PA times PB. Again, PT square equals to PA times PB. Okay, so we can actually implement rule 10 in our drawing. Why? Because in our drawing, if we focus on this common example point B, from this common example point B, we have tangent BP, that is tangent to this semicircle and this point P. And from the same common example point B, we have here chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, we get that BP square equals to BC times BA. Okay, BP square equals to BC times BA. So according to rule 10, BP square equals to BC times BA. Here you can see that BC equals to 1 and BA equals to 5 plus 1, that is 6. So here BC equals to 1 and BA equals to 6. BA equals to 6. So BP square, according to rule 10, BP square equals to BC times BA. BP is the missing tangent, so we leave it as it is. So BP square equals to BC. BC is 1 times BA. BA is 6. So in conclusion, actually found out that BP square equals to 1 times 6, that is 6. We take a root out of this equation. And finally we get that the missing tangent BP is equals to the square root of 6 units in its length. And this is the missing tangent BP is equals to the square root of 6 units in its length, according to rule 10. In the next step, I will copy the right triangle APB in a new page, and we'll implement the Pythagoras theorem on this right triangle APB. AB equals to 6 units in its length. And we just right now found out that side BP equals to the square root of 6 units in its length. So actually, this is the right triangle APB that are coming from the original drawing. Repeat again, PB equals to square root of 6 units in the neck, and AB equals to 6. So here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle APB, the square of the hypotenuse must be equal to the sum of the sides of the perpendiculars. The hypotenuse is AB, therefore the square of the hypotenuse is AB square, and AB square must be equal to AP square plus PB square. Again, AB square must be equal to AP square plus PB square. So I write it down. AB square, that is the square of the hypotenuse, must be equal to PA square plus PB square. AB is 6, therefore AB square is 6 squared, that is 36. And it is equal to PA square. PA is the missing side, so we know it as it is. PA square plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, that is 6. So in conclusion, if we found out that 36 equals to PA square minus 6, we subtract 6 from this equation, and finally we get that PA squared, the missing side PA squared, equals to 36 minus 6 is 30. We'll take a root from this equation, and we get that the missing side PA equals to the square root of 30 units in its length. PA equals to the square root of 30 units in its length. PA is the diameter of the green semicircle, and it is equal to 30 units in its length. If PA is the diameter, it means that the radius must be equal to PA over 2. Okay? So the radius of this green semicircle equals to PA over 2. We define the radius as R. So R equals to PA over 2. The radius of the green semicircle equals to the diameter PA over 2. The diameter PA is square root of 30, and therefore square root of 30 over 2 is the radius R. So in conclusion, we found out that the radius of the green semicircle R equals to square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of the green semicircle equals to pi r square over 2. So I write it down. The area of the green semicircle equals to pi r square over 2. R is square root of 30 over 2, therefore r square is square root of 30 over 2 squared. So it is pi times square root of 30 over 2 squared divided by 2. We'll open the brackets of this expression and you get that the area of the green semicircle equals to pi. Square root of 30 square is 30 over 2 square is 4 divided by 2. So it is pi, and 30 over 4 over 2 is 30 over 4 times 2. So in total, the area of the green semicircle equals to 30 pi over 4 times 2. Here, 30 over 2 is 15. So in total, this expression equals to 15 pi over 4. 15 over 4 is 3.75. So in total, this expression equals to 3.75 pi. So here, in terms of numbers, it is equals to 3.75 pi. It is equals to 11.78 square units. So, in conclusion, we found out that the area of the green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. So I repeat again, actually found out according to the second method also that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equal to 11.78 square units. So in the next step, I will summarize the lecture. We start with the first method, of course. In this lecture, we found out the area of this green semicircle using two different methods. So I start with the first method. So in the domain we have two semicircles. Line segment AC equals to 5 units in its length, line segment CB equals to 1 unit in its length, and our mission is to find out the area of this green semicircle. In the first step, we join points P and B together by a straight line. And then I copied the right semicircle with the peripheral angle that was created by joining points B and P together by a straight line. In the new page, we implemented the point rule 7 in the white semicircle. So this is the white semicircle that I copied from the original drawing. By joining points P and B, we created peripheral angle APB. AB is of course the diameter of this white semicircle. Here AB is the diameter of the white semicircle, and we have a peripheral angle APB that is subtended on AB, that is the diameter of this semicircle. And according to rule 7, whenever you have a peripheral angle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. Therefore, peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle, must be equal to 90 degrees in its size according to rule 7. Likewise, we join points C and P together by a straight line. And then I copied the green semicircle with the peripheral angle ACP that was created by joining points C and P together by a straight line, and again implemented rule 7 on the green semicircle. This is the green semicircle that I copied from the original drawing. So here we have, by joining points P and C together by a straight line, we created peripheral angle ACP. We know that AP is of course the diameter of this green semicircle. Again, AP is the diameter of the green semicircle. And peripheral angle ACP is subtended on AP, that is the diameter of this green semicircle. Therefore, peripheral angle ACP must be equal to 90 degrees in its size according to rule 7. So this peripheral angle ACP equals to 90 degrees in its size according to rule 7. So in the original drawing, you can see that this is angle A. It is a common angle. It belongs both to the green triangle APC, and angle A also belongs to the triangle APB. Therefore, angle A is a common angle. It belongs to both triangles. So we define this common angle A as alpha. This is the common angle A that we defined as alpha. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, this equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, here we define this common angle A as alpha. So in the green triangle ACP, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this missing third angle must be equal to 90 degrees minus alpha. In the next step, I copied both the green right triangle and the white right triangle in a new page, and we proved that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are copied from the original drawing. And I quote that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is the angle alpha, that is a common angle that belongs to both triangles, therefore we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the three angles in this green right triangle APC are correspondingly equal to all the three angles of this right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again. We actually proved that the right triangle APB is similar to the green triangle APC according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the right triangle over side AC in the green triangle. I repeat again. We derive that AB over AP equals to AP over AC. AB is 6 and AC is 5. So in total, again, AB is 6 and AC is 5. So in total, we actually found out that 6 over AP equals to AP over 5. Here we cross multiplied this equation and finally found out that 6 times 5 equals to AP squared. 6 times 5 is 30, so 30 equals to AP squared. We took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. Okay, but what is the missing side AP? AP, it is actually the diameter of the green semicircle. If AP is the diameter of the green semicircle, it means that AP over 2 is the radius. So the radius R of this green semicircle equals to AP over 2. AP is equal to 30, therefore square root of 30 over 2 is the radius of this green semicircle. So we know that the radius of this green semicircle equals to the square root of 30 over 2. And the area of this green semicircle equals to pi r squared over 2. Repeat again, the area of this green semicircle, that is the area that we are looking for in this question, equals to pi r squared over 2. So it is pi, r is square root of 30 over 2, therefore r squared is square root of 30 over 2 squared divided by 2. We open the brackets here and found out actually that the area of this green semicircle equals to pi, and square root of 30 square is 30 over 2 square is 4. Divided by 2. So actually found out that the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total this expression equals to 30 pi over 4 times 2. 30 over 2 is 15. So in total this expression equals to 15 pi over 4. So actually, and 15 over 4 is 3.75, therefore this expression in total equals to 3.75 pi. So actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers it is equal to 11.78 square units. So in both methods we arrive to the same result. Okay, thank you very much.